Okay, welcome back again. So, as I said on the last video, on this one, I wanted to do this operation between these matrices, multiply these matrices, but now by hand. Um, on previous videos, I was doing this operation of multiply two and three matrices, but unfortunately, I commit mistakes, but now I got it. So I wanted to show, I wanted to show to you how you can do it as well, and also add uh, something about this intro in spherical coordinates. So let's do it. First, I wanted to draw a sphere. Okay. So first is a circle, and now the shape of a sphere. And why this? Because this way I can illustrate better how these transformation are being made. Okay, so I'm also going to copy this. And I don't know if you already can see, but right here is already representing this piece of the sphere. And what is nice is we can see the difference. Both of these transformations, the Cartesian, the cylindrical, and the spherical one, are needed on the 3D space, but the accuracy, um, how a rigid body can move on the 3D space um, depends upon on the robot that we are using, but this robot needs to have specialized parts to be able to do certain uh, movements. Um, and this depends on joints, on links, and we are talking about Cartesian coordinates. So right here, for example, so is a robot that can do three transformations of translation. So it is limited. And how can I explain this to you? Um, Let me draw a vector, and again is a analogy to a robot arm. And but if I make this bigger, maybe I can demonstrate this to you. Let me copy this. So I'm gonna copy, and Also, I'm doing this in real time as I'm recording this this video, so I'm not so sure. But for example, we have this robot arm. So right here, we are limited in three transformations of translation. So what I'm going to do is to translate this robot arm alongside above this axis. So I can illustrate this, try to illustrate a robot arm just for illustration purpose. So right here we have a robot arm, and this robot arm, as we already saw, is limited on 4, 3 transformations of translation. Okay, so let's translate this robot arm alongside this axis. So it can be moving. We can translate to here. So we are doing a translation alongside or above the z-axis. So this robot arm is going to be localized on this point. And of course, this is a coordinate system. The Cartesian, the spherical, the cylindrical, both are coordinate system. And this geometric solid, it represents the way that these transformations can be done on the three-dimensional space. So right here, again, we are limited of three transformations of translation. So this we cannot change the orientation of this um, robot arm. Um, we can do again a transformation uh, to here, and we can go to the y-axis. So right now is localized on this point, but we are limited. And if I wanted to, my robot arm um, got pointed to here. Okay, so how can I do this if my robot arm is limited of just transformations of translation? And that is okay, because um, it depends on the application of the robot. It depends of the task that this robot is doing. So all is going to depend um, on the task that we wanted to that a robot perform. Let's say it is a task of pick and place. So this type of robot is already enough to 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 uh, to do this type of task. But let's say is a more complex task, so in which we need that this robot can change its angle. And right here, we are not working with angles. Um, and this, again, it depends on the application of this robot. So if it is just a task of picking place, this type of robot is already meeting our requirements. And again, as we already saw, we have a task description, and on this text description is described the task that this robot it has to perform. And as we saw, is a sequence of transformation. So let's say n we can have more than three transformations. Right here we are limited on transformations of translation above the x, y, and z axis, but we can go to here. So we we made a transformation, and down a second transformation, and to here a third one, a fourth. Okay, so that is how this robot arm is moving on this coordinate system, which is the Cartesian coordinate system. And this is a simple, the most simple illustration. Actually, I wanted to draw a pick and place robot. Pick and place is just a task, but this robot can do um, more than one task. It can be, as we already saw, a task of drill, but this also it depends on the scenario in which this robot is located. Where is it its constraints? So I will try to draw right here, and this video it was to just to calculate do the operation of multiply those matrices, but if get very long, I can do another one. And crossing this rigid body, which is a part of this robot, another piece of it. Okay. And now it's very straight. Another rigid part. Okay, and as you can see right here, so let's place also the tool that this robot is carrying to perform the task, and it can be the most simple one, just a hand. So it's a pick and place task, for example. I don't know. And as you can see, we are limited on the Cartesian coordinate system. So right here, let's see the most obvious path for this robot, for this for the hand. So let's say this rigid part is a robot which that are made of three parts, three rigid bodies. So is going to up here. So is a transformation on the z-axis. And when this, let me see, but because this this hand can be fixed on this part. Okay, so it goes to here, so it's on this point. So let's say it reach till this point, and when it was on this point, it performs another transformation on the x. Let me see. Okay, on the x-axis, and right here, when was right here on this point, it goes. Let's see, it can goes to this point on the y-axis. Okay, let me run with this. I will reuse this illustration, and now let's illustrate um, for the cylindrical one. And for the cylindrical one, let's draw a cylinder. Okay. And let's see, for the cylindrical one, we can have two transformations of translation and one transformation of rotation. So is a robot, we can say that is robot for certain type of task, and also is in some way limited, and on this case is also limited in the way this robot can change its orientation. And you will see that from the spherical one and the articulated, we can change the orientation of the robot. So this part we can eliminate it. Eliminate. Okay. And right here, I have to draw this a little longer. And now I will place right here. Above this cylinder. So we can illustrate its transformations is two translations and one rotation. So again, let's see what is the most obvious path for this, for the hand of the robot. We can go up to here, on the z-axis. So it can go up and down, and these are transformations. Um, and we can translate on this x-axis, so it can go um, to the right, to the left, and this for any time that is necessarily. We cannot we are not limited on the quantity of times that we do transformations. We are limited on constraints, and we can do a rotation one. So this whole set, it can rotate, but I don't know how can I rotate this. Just if I'm do another draw, let me do this very quickly because I don't wanna that this video got very long, yes, very long. So let's say it is rotating some angle, so it goes to here. Something like that. I don't know. And can you see? This way. So after a rotation, um, now the hand of the robot, the end effector is on this point, is localized on this point of the cylindrical coordinate system. So both are both the Cartesian and cylindrical coordinate system. Uh, it don't allow us to do change on the orientation of the end effector. Um, Again, let's say that I wanted to my end effector point to this point or to this in any direction that I want. We are limited uh, with this coordinate system, the Cartesian and the cylindrical one. On this coordinate system, it is not in a sense the transformation, because we will do transformations of translation and rotation on, let's see, the spherical one. On the spherical one, we do two transformations of rotation and one of translation. So notice, it's not the transformation, is the coordinate system. So this two coordinate system is limiting us and change the orientation of the effector of a actuator. Very nice. And I draw this sphere because, as you can see, now we can have a vector, and let's say is on the center of this sphere. So it can be pointing to here, to here, to here, to any point. So from the spherical coordinate system, now we have the ability to change the orientation of this end effector of the actuator, and only with this coordinate system and the articulated one we can do this type of change on the orientation. And this is very important when we are picking a robot to be applied in some certain task. So we have to do this type of analysis, and also is a work of economy, because we will not buy a robot to be applied on a task just of picking place parts. And also, we will not buy a robot of picking place work task to do a work that is a work for a robot in that can move on the spherical coordinate system, or a articulated one. You will just waste money. Okay, so and we have these vectors beta and gamma, and those are for the two rotations, and R is the ratio that is this mechanism, this device, this robot can reach. Okay, so we will see more of this theory as we approach robot examples, as we get throughout the book, as we got more deeply. So I wanted to do this operation with you by hand, very quick. So this first one, okay, so is a line multiplied by each column. Let's see, this line multiplied by each column, and so C gamma minus sinus gamma 0 0 sine of beta, sine of gamma, sorry. So cosine of gamma times cosine of beta plus sine of gamma times 0 plus, and 0 will cancel these terms. So right here we got just cosine of gamma times cosine of beta. So right here, cosine of gamma, cosine of beta. Now this column, zero, 1, 0, 0, so it's going to be just sine of gamma. Okay, now so cosine of gamma times sine of beta. And right here 0, 0, 0. So it's just cosine of gamma times sine of beta. And right here is 0. Now is this line with each column. Sine of gamma, cosine of gamma, 0, 0, cosine of beta, 0 minus sine of beta and 0. So it's sine of gamma times cosine of beta. And right here, sine of gamma, cosine of beta. Okay, and now 0, 1, 0, 0. So right here is cosine of gamma. And now sine of beta, 0 cosine of beta, 0. So it's sine of gamma, sine of beta, sine of gamma, sine of beta. And right here is 0. Now the third line, 0, 0, 1, 0. So right here is minus sine of beta. Right here is 0, cosine of beta, and 0. And now the last line, 0, 0, 0, 1. Right here is 0. Right here is 0, 0, and 1. Okay. Now let's multiply with this another matrix. So this line with each column, so cosine of gamma, cosine of beta, minus sine of gamma, cosine of gamma, sine of beta, 0, 1, 0, 0, 0. And let's see. So is just cosine of gamma, cosine of beta. And now this column, which is going to return to us, let's see, 0, 1, 0, 0. We will return minus sine of gamma. Okay, and now this third column, 0, 0, 1, 0, which will return cosine of gamma, sine of beta. Okay. Now the last column, 0, 0, or 1. So is cosine of r times cosine r times cosine of gamma, sine of beta. Now the second line, sine of gamma, cosine of beta, cosine of gamma, sine of gamma, sine of beta is 0, 1, 0, 0, 0. And right here we are left with sine of gamma, cosine of beta, and the rest of the elements are 0. And let's jump to the next column. 0, 1, 0, 0, and 0, cosine of gamma, 0, 0. Oh, sorry, let me do it again. The second line, the first column, is sine of gamma, cosine of beta. Now the second column is cosine of gamma. The third column is sine of gamma, sine of beta. And right here is r sine of gamma, sine of beta. Now the third line minus sine of beta, 0, cosine of beta, 0, 1, 0, 0, 0. So we are left with minus sine of beta, and now multiplying by the second column, 0, 1, 0, 0, and we are left with 0. Now the third column, 0, 0, 1, and this is cosine of beta. And now the last column is r times cosine of beta. Okay, let's see, we are getting there. Let's see if I'm not commit a mistake as the last time that I was doing these operations. I was doing these operations. Okay, so now this is 0, here is 0, 0, and 1. Okay. See how by hand it takes a lot of time, and use the octave is a one more tool for our set of skills. Okay, hope I not commit some mistake. And if I commit, this is why we are using octave. It's alright. So let's compare. Right here. Okay, there we go. It's all right. So with this video, the main thing that I wanted to comment with you, it was about this sphere, and also to give a sense types of robot that we can apply in different types of tasks. And as I explained to you, only the spherical and the articulated coordinate systems, only on these systems we can change the orientation of the robot. It's not the transformations, it's the coordinate system. So as this is a sphere, now we can put the end effector right here, right here, right here, right here, and we can do a transformation that this end effector is going to this point, and it can translate up here. So a spherical one and articulated one, it gives us more, they are not limiting us on the 3D space. So it's not the transformations, is the coordinate system which limit us, and the transformations together with the coordinate system tell to us how this robot can do a movement on the 3D plane. It describes all his motion. And in addition, we write transformation equations. And right now, I'm pretty sure that you are almost advanced on robotics topics, on robotics subject. And now we will solve a example. Is the 2.12 from the second edition and 2.19 from the third edition. But this only on the next video. And so we can start to discuss about articulated coordinates and then about forward and inverse kinematic equations. Okay, for now that's all, and thank you for watching, for following this series. Thank you for follow this series, and that's it. Bye bye.